As we discussed before, the output of a rectifier is not suitable as a DC supply to loads. This is because it has too much variation. A solution exists in connecting a capacitor across the load resistor. To see how this works, consider this simplified circuit first. This has no load resistor, but only a capacitor. Let us look at the positive half cycle and start drawing the output. As Vi goes positive, we see that the diode conducts and the capacitor is charged so that V0 equals Vi. This goes on until Vi reaches its peak value, Vp. After that, as Vi decreases, the diode becomes reverse biased. Its cathode here is at a higher potential than its anode here. The output voltage, however, remains constant at the value Vp. Theoretically, the capacitor will never get discharged, and so you will have a waveform like this. The circuit provides a DC voltage output equal to the peak of the input sine wave. This is, of course, the ideal situation. Realistically, we have a circuit like this. For simplicity, we will assume the diode to be ideal. As the input voltage increases, the capacitor gets charged to the peak voltage Vp. Then, as the input voltage decreases, the diode gets cut off, and this time the capacitor starts to discharge. Look here. The capacitor will keep on discharging until Vi starts to increase again and becomes greater than the capacitor voltage. This point here. The capacitor will again get charged for a little while till here, when again Vi starts to decrease and the diode is off. So the cycle repeats itself. To prevent the output voltage from decreasing too much, we have a high value of C, the capacitance, so that the time constant, which is equal to Cr, is much greater than the discharge interval. Now let's look at some equations. IL, which we can also take as IL, which is also equal to IR, is equal to V0 over R. ID equals IC plus IL. We apply Kirchhoff's current law at this point, and the value comes out to be C dVi by dt plus IL, where this expression here is the standard for current through a capacitor. Remember, we are assuming that Vd equals 0. Now let's look at some features of the graph. The diode conducts for a brief interval delta t near the peak of the input sinusoid and supplies the capacitor with charge equal to that lost during the much longer discharge interval. The latter is approximately equal to the period t. During the diode off interval, the capacitor C discharges through R, this portion here, and thus V0 decays exponentially with the time constant Cr. The discharge interval begins just past the peak of Vi. At the end of the discharge interval, which lasts for almost the entire period t, V0 equals Vp minus Vr, where Vr is the peak-to-peak ripple voltage. When the time constant tau, which is equal to Cr, is much larger than t, the time period, then Vr is small. When Vr is small, V0 is almost constant and equal to the peak value of Vi. Look at the graph here. When this interval is reduced, this one, then V0 equals Vi. Therefore, in our design, we always strive to keep the peak-to-peak ripple voltage as small as possible. During the diode off interval, that is when the capacitor is being discharged, V0 can be expressed as, at the end of the discharge interval, we have Vp minus Vr is approximately equal to Vp e power minus capital T over Cr. The approximate sign is because the discharge interval is approximately equal to t. Now, since Cr is much larger than t, we can use the approximation e power minus t over Cr is approximately equal to 1 minus t over Cr. And hence we obtain Vr equals Vp t over Cr. It agrees with our earlier assertion here. This circuit is known as a half-wave peak rectifier. This is just like the circuit that we drew in the lecture. So let's play it. And here you can see that the output, the straight line, is slightly less than the input, which is the sinusoid. So in a way, it is an approximation of the peak of the sinusoid. However, notice that our Cr, which is a product of the capacitance and the resistance, is very high. Now, because of this, we can see that the output is an almost straight line instead of the slanted one that we had seen in our lectures.